Hello everyone, and welcome to my channel. This channel is for educational purposes, and we look at theories of everything that you probably haven't heard of before. We take deep dives into them so that you can probe into how you might be able to use these to benefit your own life, to help you with your paradigm shifting, to awaken your 5D consciousness, to help you create a holistic worldview, a more healthy lifestyle, and so on. Today is our 436th video that we've done on the reciprocal system of theory from one Dewey Bernard Larson. And Larson was an American engineer who lived in the 20th century. In 1959, he proposed his two fundamental postulates about how he believed the universe operated. And then from those postulates, he deduced a theoretical universe about what the universe would look like if his postulates were correct. And then in some books, he compares his theoretical universe with the measured universe of the astronomers and the chemists and other laboratory studies compiled in tables that he was able to get his hands on. And we're looking at one of those works today called Basic Properties of Matter. This is a book on chemistry. And we are in chapter 4 called Compressibility. So Larson arrives at a number of different equations for various aspects of pressure and compression and compressibility, and compares his goes through his theoretical derivation, which is oftentimes difficult to follow because, you have to know many of the finer points of the reciprocal system. But if you can kind of glean where he's going, then you can try to figure out how he derives his equations, and then he makes his calculations and compares them with the observed values that are in the tables. And basic gist of Larson's reciprocal system is also known as a universe of motion. Larson's idea is that the universe is made entirely out of motion, not matter, not energy or force or anything, but it's made out of motion. And for Larson, motion is the relationship between space and time, which makes sense because if you look at speed, basic kind of motion, cars moving 10 miles per hour, 10 miles of space in 1 hour of time, space over time. That is a relationship between space and time. And he imputes a generalized reciprocal relationship between space and time. If you decide to double the speed, you can now say the car is moving 20 miles per hour. Or you can say equivalently that the car is moving 10 miles per half hour. You can multiply the space, or you can divide the time. That evinces or evidences a reciprocal relationship between space and time in speed. Larson generalizes that to be just more than speed, but all forms of motion, of which he includes really all of our scientific phenomena, such as matter, energy, force, acceleration, momentum, power, pressure, viscosity, fluidity, electric charge and current, electric capacitance, and magnetic flux, and permeability and permittivity, and many other different motions that he identifies as fractions that have space or time as the numerator and time or space as the denominator, with the caveat that space or time, space and time both are multidimensional. They come in 3 or maybe even more dimensions. Larson says 3. And so that's where he gets the name the reciprocal system of theory. Now, when Larson says that the universe is made out of motion, he's referring specifically to a motion that he calls scalar motion. This is a little bit different than what we're accustomed to, but it can be envisioned using a balloon that you put dots on, or spots. And you blow up the balloon, all of the spots will be moving away from each other, but not in any specific direction. Every spot will be moving away from every other spot. And even the locations between the spots will all be moving away from every other location. So this is a kind of non-localized or non-directional motion. It has no specific direction. If you contract the balloon and make it smaller, then all of the spots will be moving toward each other. So the scalar motion basically only has a direction in or out, but not a specific direction of like this dot is moving in this particular direction. They all are moving in all directions, which is a little bit difficult to kind of grasp, but you can kind of see it if you arbitrarily decide that you're going to declare one of the dots motionless. When you do that, then you can start to impute directions to the other dots. And it also looks like there is a force field between one dot and another, but between really all the dots and the one that you decide is motionless. It looks like that one that's motionless is emanating a force field, and all of the other dots are attracted to it. But that's not the case, or maybe that is the case, but it is the result of assigning a reference point, not a result of the motion in general. The motion in general has no specific direction. So that is a scalar motion, but in particular, that is a one-dimensional scalar motion. And in Larson's system, there are 3 dimensions. Another major aspect of Larson's system is the discrete unit postulate. There is space and time and motion are quantized, meaning that you have to have a minimum unit of space or time or motion in order to have that quality at all. And if you have exactly 1 unit of space in 1 unit of time, again remembering that space over time equals speed, you have the what Larson calls unit speed. 1 over 1 equals 1. And unit speed is also known as the speed of light. Now, what you have to get with the reciprocal system is you have to be able to conceive of a universe that has a motion without anything moving. The motion comes before anything that would be moving. So you have to be able to envision an empty universe with nothing but motion. And that is this unit speed, or what Larson calls the progression of the natural reference system. That outward motion of the balloon is what Larson calls the progression. The inward motion of the balloon is what Larson calls gravitation. And the progression at unit speed, 1 unit of space per 1 unit of time, which is also known as the speed of light. So an outward motion or a progression at unit speed, the speed of light, is the background motion of this universe. It is omnipresent and eternal, always there, always occurring, no matter where you go in an empty universe. And in at any time or place in the universe. This motion is always occurring. And this is really the source, the 0 point, the null point, or the neutral point of the universe, from which all other phenomena evolves, we'll say. And Larson calls this the progression of the natural reference system. So he has a natural reference system from that the universe conforms to, that is different than reference systems that we might assign arbitrarily. This is the natural reference system. So Larson has the progression of the natural reference system. As a result of this discrete unit postulate, this is the center of the universe, and that means that there is half of the universe that's moving slower than the speed of light, and half of the universe that's moving faster than the speed of light. Larson refers to these as the material sector and the cosmic sector, respectively. The cosmic sector is something that is pretty much unknown to science, whereas the material sector is well-worn and fairly well understood. In the material sector, you have basically, this is where we reside. And this is the realm of what he calls the spatial reference system. And the spatial reference system is basically coordinate space, 3 dimensions of space, x, y, z coordinates in a still frame, and a progression of time. Time is moving in a scalar manner, always getting later and later, further and further apart in time, but in no specific direction, in a scalar, like on the surface of an expanding balloon. But space is more like an abstraction, more like taking that spot and arbitrarily assigning it to be motionless and anchoring ourselves at that point. And so we see space as this motionless thing that has 3 dimensions of extension, x, y, z coordinates. And but we see a progression in time. But if we moved over into the cosmic sector, crossing that boundary, that unit speed boundary into the cosmic sector, then the rules would reverse, a la a reciprocal. And we would observe 3 dimensions of time in a still frame and the progression of space. Space would always be getting farther and farther and farther apart in a scalar manner, like on the surface of an expanding balloon. So when we cross that boundary, the functions of space and time invert or interchange. Now, also, within the material sector and the cosmic sector, both, there is an inside region of both. One is called the time region. And in the material sector, the time region occurs when you don't have a full unit of space. A unit of space is approximately equal to 1/500,000th of an inch, or 2 millionths of an inch. And within this space, you don't have space because you have to have a full unit. And so if you don't have space, then you only have time, because the universe is made out of motion, which is space and time only. And so if you don't have space, you have to have time. Larson calls this the time region. This is the realm of interactions between atoms and molecules that occur in less than 1/500,000th of an inch. And when you cross this boundary into the time region, then you are, first of all, dealing with this temporal reference system instead of the spatial reference system. And you invert the rules. And so now the progression is moving inward while gravitation is moving outward, at least as far as the equivalency is concerned. We have to remember that we are anchored to a spatial reference system. So we really only see space. We don't see time. And so even though everything in the time region is going on in three-dimensional time, we don't see it that way. We see it in what he calls equivalent space. We see the inverse of what's happening in time in equivalent space, but it is reduced by the a second power relation. What we see in equivalent space is a second power quantity, and we also see only a fraction of what's actually happening. Much is lost in the translation of crossing that boundary. He calls that the interregional ratio. So these are factors that have to be taken into account when you look at things like compressibility. Now, the same thing is happening over in the cosmic sector, with the space region being within a unit of time. A unit of time is approximately 1.5 times 10 to the minus 15 seconds, and inconceivably short amount of time. But within that amount of time, there is no time and there is only space. And once you cross that boundary, then everything is moving, the progression is moving inward in time, and gravitation is moving outward in time. Now, again, that's, the equivalent of time. Now, when you have those dynamics where the progression is moving inward and gravitation is moving outward, and you look at something like compressibility, the gravitation is pulling particles away from each other, but the compressibility is pushing them closer together. So you have what is called an internal pressure, because that progression is always present. It's omnipresent. And so it's intrinsic to the time region environment that there is, or to matter, that there is an internal pressure between two interacting particles. Now, Larson's atom is a little different than in mainstream science. In legacy science, there is a periodic table that has a number. Every element has an atomic number. In Larson's system, every element has 3 numbers, and these are rotations. Rotations of the 2 basic photons that are at the core of every atom. And the photons come about, they are basically motionless particles that are carried by the progression at the speed of light. They are what he calls simple harmonic motions, or vibratory motions. And then those vibratory motions are rotated, which is a manifestation of gravity. And they are rotated in 3 dimensions, because there are 3 dimensions of motion, not just one. And that is where Larson gets his notation for each atom. So each element has first a 2-dimensional rotation, and then a second or secondary 2-dimensional rotation, and then an optional 3-dimensional, an optional third number. Well, the number, it can be 0. I'll just say that. It can be 0, or it can be positive or negative. And the third number is a 1-dimensional rotation. So you have 2 2-dimensional rotations that alternate, and then a 1-dimensional rotation that can be positive, negative, or 0. And then Larson permutates those numbers to come up with his rotational factors for various things, and then plugs them in his various equations here for compressibility and other things. Now, in the solid state, an equilibrium is established, and Larson's atom is really the nucleus of legacy science is atom. Larson doesn't believe in the nucleus. He believes that the atom itself is the nucleus, and this electron cloud that creates all this space in the atom is non-existent, but that atoms, whereas the legacy scientists believe that atoms are in contact in the solid state, Larson believes that they establish an equilibrium of kind of bonding in the solid state, and they have a distance, that every atom is a distance apart from every other atom, and that is an equilibrium that is established called the interatomic distance, and that is established where the progression moving the atoms toward each other is in equilibrium with gravitation, which are moving them apart. And again, remember that the progression is constant and ubiquitous and eternal. So it's always there and it's always the same. But the gravitation is varying depending on the inverse square law. So every atom has a different interatomic distance. This was a subject of his chapter 2. And so when you have the when you add in this compression, then that decreases the interatomic distance, and subsequently it decreases the volume of the atom. So in this table, he's looking at relative volumes under compression, and so he's looking at the compression. He goes in kilograms per square centimeter, but I think that's pretty much the same as atmospheres. And he's looking at the number of atmospheres that he's doing this by the I think the thousands of atmospheres, and looking at the various atoms, calculated. It's hard to read this chart, but he's pretty much exactly on the mark with many of his calculations. Observed 0.984, calculated 0.984, observed 0.990, calculated 0.989, depending on what the element or compound it is that he's talking about. As we move up and go into higher pressures, all the way up to 60, 70,000 atmospheres, he's still certainly very close to the mark, although there are some discrepancies. But some of these discrepancies also are just endemic to the laboratory procedure, in that, like, if he cites two different laboratories, they will also have discrepant results by the same amount that Larson is getting here. So he'll probably be explaining it right here. Well, he's going to lead us into another table. Table 16 extends the volume comparisons to representative elements of the classes that are subject to transitions within the experimental range of pressures. Again, there are two different kinds of transitions that elements and compounds undergo under pressure. One is the adjustment of the crystal structure being the solid equilibrium arrangement and the bonding arrangement. And then also under pressure, where pressure is a two-dimensional thing and the volume is a three-dimensional thing, the amount of the compression that is being resisted by the rotational forces or the gravitational forces of the atom is related to the orientation of the atom, because when the atom is three-dimensional and the pressure is only two-dimensional, it depends on how the atom is oriented or directed to figure out how much is resisting that compression. And as more compression comes in, more and more of the rotational factors are employed to resist that compression. So that also causes discontinuities in these compressibility curves. And these curves basically take the shape of multiple line segments, and there are spots at which there are inflection points, and they are and those are the points where these different transitions are occurring. Okay, so transitions reported by the investigator or indicated by the theoretical calculations are shown by horizontal lines in the appropriate columns. In these tabulations, the position of the upper branch of each curve has been fixed by using the experimental volume at a selected pressure in the straight line segment above the transition identified by the symbol R as a reference point. Thus, the shape of this upper branch of the curve is determined theoretically, but its position relative to the 1/volume squared scale is empirical. Again, the volume is squared because there is a two-dimensional relation in the time region in equivalent space. Some work has been done toward extension of the theoretical development to a determination of the exact position of the upper section of each curve, but this project is not far enough advanced to justify any discussion of it at this time. Okay, then he has another chart, and he's looking at atoms such as silicon, calcium, whatever element is SB, don't remember that one. And he's looking at the relative volumes under pressure again, depending on the atmospheres. And, obviously the volume is getting smaller and smaller as we get larger and larger pressures. At zero pressure, the volume is 1. And then it reduces by the time you get to 60,000 atmospheres. With some of the elements, the volume is at about 0.95, but with some of the atoms, the volume is all the way down to 0.78. At 100 atmospheres, the volume in some is down to 0.70, calculated at 0.701, and observed at 0.702. I think that is barium. And then he points out areas where there's transition curve, where there are inflection points, where transitions are being made. And then he goes to other elements, shows what their compression factors are. Those are the rotational factors that are resisting this compression. And he examines a number of different elements here. And it looks like most of his results are very close to the observed values. Compressibility patterns of compounds are theoretically identical with those of the elements. And this theoretical conclusion is confirmed by compression data for a representative group of inorganic compounds presented in Table 17. So Table 17 is pretty much the same, except that he's looking at inorganic compounds, NaCl, NaI, KCl, zinc sulfide, and, I think the theoretical considerations are pretty much the same. He identifies various transition points, and just making measurements that are, again, very close to the observed values, so it appears. I'm just trying to see if there are anything kind of worth commenting on here. It looks like everything is pretty close to the established observed value. And he goes through some more compounds here: silver chloride, cesium bromide, and some other organic compounds. Not seeing anything like terribly noteworthy here. As might be expected for the less uniform composition, transitions are somewhat more common in the compounds, but otherwise there is no difference in the compression curves. The curve for potassium chloride, shown graphically in Figure 1 and by numerical values in Table 17, is of special interest because it includes a sharp first-order transition in which there is a substantial decrease in the basic volume. That's again from the change in the crystal structure, while the compression factors remain unchanged. So that's what causes a second-order transition, the compression factors. The first-order transition is caused by the alteration of the crystal structure. The magnitude of the volume reduction that takes place indicates that there is a reorientation of the atomic rotations in which the neutral specific electric rotation 5 is substituted for the normal rotation 4 as the effective relative value. The theoretical volumes beyond the transition point are shown in the table based on the small atomic volume corresponding to the higher rotation, up to 20,000 kilograms per square centimeter. The volume follows the curve corresponding to compression factors 421, and sulfur trioxide equals 1.222, which produce an internal pressure of 112.7 mega kilograms per centimeter. At the transition point, the basic volume drops to 0.976, increasing the internal pressure to 141.1 mega kilograms per square centimeter. The compression then continues on this basis up to the vicinity of 45,000. Where the compression factors change from 421 to 431, and the internal pressure rises accordingly. Okay, we're going to stop there right now. Again, don't get lost in the weeds here. I mean, these are very much finer points of Larson's system. I go over them because they're part of the text, and I'd like to read that into the record, but also just to give you an idea of how he's thinking and what the process is and what's going on with the reciprocal system. The important thing is just to remember the basic ideas, and then, glean a few things here or there from this, and that is enough. So hopefully you can tune in tomorrow,